Welcome, everyone. Welcome to the Southeast Key Message 2 this afternoon, covering increasing flood risks in coastal and low-lying regions with Doug Marcy. And my name is Aranza Sud-Laskarine, and I am the Assistant University Director here at the Southeast Climate Adaptation Science Center. And thank you for joining us for a webinar series on the 4th National Climate Assessment, commonly referred to as the NCA4, where we're specifically exploring the Southeast chapter. And we will be focusing on one key message per month, ending with the Tribes and Indigenous Peoples chapter in January. We've also added in February an overview of the Caribbean chapter by Bill Gould, so stay tuned for information about that one. We wanted you all to hear directly from each of the key message lead authors with the opportunity to have a Q&A with them and at the end of the presentation. Please keep in mind that we also want to make sure that the audience knows how to use all the components and data within each of the key messages. So to that end, we will launch just a real quick poll, and thank you in advance for participating. This poll helps us know how best to continue disseminating the NCA4 material. So you will see that pop on your screen, and you can click on your affiliation, and then on question number 2, a little bit about your knowledge of the NCA4. Okay, all right, just a few more seconds there. We've got a few people coming online. But this really gives us and the authors an opportunity to see sort of your affiliations and what intersection with the NCA4 might be of interest to you.
Okay, a few more seconds and we're going to go ahead.
Okay. All right, and Doug, that gives you a little bit of an idea there of our demographics.
Okay. Although I'm having a tough time seeing that because I think maybe it's because I'm sharing my screen.
Oh, okay.
But that's okay.
Okay, well, basically we've got a large percentage of university participants followed by state agencies and then federal agencies.
Okay.
And great. Yeah. And about 47% say they've used the findings from the report in some way. So that's good news.
Okay, good.
Okay, and then also just to tell you this, an equal number haven't really yet used the information. So we've got about 50-50 here. 50 have, 50 haven't, and a little bit have already downloaded even some data and graphics.
Great.
All right, well, with that, thank you so much for participating in that quick poll. I'd like to introduce today Doug Marcy. He is a coastal hazard specialist at the NOAA Office of Coastal Management in Charleston, South Carolina. He has been with NOAA about 18 years working on flooding and sea level rise geospatial mapping projects, storm surge assessments, and coastal hazards assessment projects, contributing to more disaster resilient communities. He's also worked with the U.S. Army Corps of Engineers, the Charleston District, as well as the South Carolina Office of Ocean and Coastal Resource Management. Doug has an MS in Marine Geology and a BS in Geology from the College of Charleston. Doug's current interests include using geospatial technology combined with meteorological, hydrological, and coastal modeling, including sea level change, to enhance inundation forecasting, mapping, and risk assessment. And if I would, I'm just going to read a couple of sentences here regarding the purpose of the National Climate Assessment, just so everyone is aware. The National Climate Assessment comes about through the U.S. Global Change Research Program, or known as the USGCRP. It was established by an act of Congress in 1990, and among the mandates in that law was a requirement for a quadrennial assessment of how climate is changing and how those changes are impacting a variety of sectors across the country. Over time, stakeholder demand for and scientific advances have allowed an increased focus on more localized information. So the fourth National Climate Assessment emphasized regional information from its inception through extensive stakeholder engagement and a structural decision to make the regional chapters more detailed. So with that, you can take it away, Doug, and just to say that after your presentation, we'll have the opportunity to engage with you for about 15 minutes or so on some Q&A. So thank you, Doug.
Okay, great. Thank you for the introduction, and thanks for inviting me to talk to everyone this afternoon. Again, and at the end of this, I'll put up a slide. We'll put up a slide of all the authors involved in the Southeast chapter. I was involved in mainly the key message 2, which I'll be talking to you about today, which really focuses on the coastal effects, well, mostly for low-lying areas in the Southeast, the impacts of coastal flooding, but also inland flooding as well. So the title of the presentation looks at coastal effects, but we will be talking about some of the inland riverine and flood events that we've seen in the Southeast recently. So to get started, I'm going to spend a little bit of time kind of going over some of the background. Oops, see if I can. Okay, there we go. Some of the background climate information that is driving some of the issues we're seeing, especially in the Southeast with sea level rise, and get into sort of the science behind some of the sea level rise, especially local sea level rise, and then get into the actual key message and go from there and start to show you some of the figures that were as part of the chapter and the key message too. So here we have what's been going on. Again, most of these graphics I'm using are actually from different parts of the NCA4, or which the Southeast chapter, which actually part of volume 2, which focuses more on the risks associated with the changes we are seeing. If you're also familiar with another volume 1, which is the climate change special report, climate science special report, I'm pulling some of the graphics from that as well. And that really gets into what the climate science is showing us. And so the sea level rise components, for instance, there's a chapter 12 in the CCSR. Well, I'll be borrowing graphics from that as well. And you'll also see some graphics and some content from volume 2 coastal effects chapter, which is more of a national chapter looking at across the country, the effects we're seeing on the coast, which is chapter 8. So you're seeing here that we have an increase in not only land temperature since the late 1800s through various, this is showing 4 different data sets, and they're all pretty much similar, showing the same trend. And I apologize in advance, I have a little bit of a stuffy head from a cold, so I'll try to articulate well. The sea temperature is also increasing. So there's a direct correlation between what's going on with land and ocean, and we think that the ocean's actually absorbing quite a bit of heat as well. What we're concerned with in the future is that how far out we're going to be looking by 2100 or so. What is the future temperature going to be? So we can track what temperature has been. And what the climate assessment tries to do is look at these different scenarios, or they're called representative concentration pathways. And the worst case here is the 8.5, and then you have these 2 other scenarios, 4.5 and 2.6, which is kind of a range of the worst case is sort of the runaway greenhouse gas scenario. We're not going to do anything, all the way down to 2.6, which is a very kind of conservative. If we stopped producing greenhouse gas right now and actually start to reduce it, we could potentially keep temperature from not going above 2 degrees Celsius more than it was from 1900. So somewhere in the middle of there is where we're going to end up probably, and that's going to eventually drive what's going to happen with sea level rise. As we know, sea level has gone up and down in the past, even before man was ever here, even before we were producing and, adding human contributions to greenhouse gas through a natural climate cycle. On the order of about every 100,000 years or so, we would have a decrease or increase in temperature that would cause an ice age. We are coming out of the last ice age, was about 14,000 years ago, and we are the last, I guess, about 4,000 or 5,000 or 6,000 years. Sea level has been fairly steady until the late 1800s, where we're seeing a definite increase in the rate of sea level rise, which you're seeing here at the bottom. What causes sea level to change? As I mentioned, it is definitely related to the temperature. And the reason that is most of the global sea level we have seen so far since the late 1800s is because the ocean is actually warming and absorbing a lot of this heat. And as the ocean warms, it expands in volume. So that will cause an increase, and that's been the increase, a lot of the increase we've been seeing. But you also see locally a lot of the contribution is from actual land subsidence, places especially like Louisiana, where we're seeing a high subsidence rate. In addition to global sea level going up, the land is going down, and so that's causing upwards of 3 feet of sea level in the last 100 years. Then we have other places like on the East Coast where we're more along the lines of 1 foot in the last 100 years. You have other contributions too, including oceanographic variability, things like El Nino, Atlantic decadal oscillation, and then of course the contribution of the ice sheets. Mostly the land-based ice is what's adding to the volume of the ocean. And as the mass of the ocean, of the ice sheets changes, that's going to redistribute how the water sits on the planet, and that's going to change things too. The greatest source of uncertainty with all these projections, and I'll show you the projections in a minute, really comes down to how much the ice sheets are going to, how fast and how much the ice sheets are going to melt. And is it going to be a linear process, or is it going to be more of a non-linear process where there's a tipping point? From the right here, you can see that most of the sea level rise globally we've seen has been from ocean expansion, some from Greenland. We're seeing more and more contributions from Greenland every year. As a matter of fact, I think this year we actually had the highest, either tied or had the highest amount of ice melt in Greenland we've ever seen. Less so from Antarctica at this point. And sea level is not rising at the same rate everywhere, depending if you take kind of a snapshot or look at a 10-year average, which is what this is showing you, that across the planet, the water does stack up on one side or another of the ocean, usually due to the dominant winds going on, like trade winds. And this is an example where up until about 2016, the Western Atlantic the Western Pacific had a much higher sea level rise anomaly going on, and this kind of variability will also be factored in. And as I mentioned, land motion plays a big part of this too. So if you look at the United States, just the continental United States, you can see the various sea level rise trends where we have rates that vary from very high down in Mississippi. Whoops, excuse me, I'll go back up. I'm sorry, down in Louisiana with these red arrows, upwards of 3 feet in the last 100 years. But there are places up in the northern parts of the country, up into Canada, where sea level is actually falling. And we don't have Alaska on this, but areas where we're seeing a lot of uplift, either from tectonics or rebound from the lack of glaciers being on the crust. The crust is rebounding, and we're having a relative low sea level rise rate, or even sea levels going down. So it depends on where you live. You'll have a different sea level rise, local sea level rise signature. An example of kind of drilling down, this is for North Carolina at Beaufort. We've had the tide gauge there. NOAA maintains the National Water Level Observation Network NLON stations, and there's about 220 or so of those around the country, basically monitoring water levels, mostly to define tide datums like mean high water or mean low water, but we also can establish these trends. The Beaufort gauge has been around since a little bit after the early 50s, and we can do a trend line, and you can see there is a lot of variability. That's the blue line going up and down, but we can draw this trend and see that we've seen about a foot rise in the last 100 years, but 41% of that is actually also due to vertical land motion. So it is a combination of the two. As I mentioned, the science that is going into NCA was a lot of that coming out of Chapter 12 of the CCSR, and a report that one of my colleagues, Billy Sweet, was the main author of. It's a NOAA 2017 report with various other authors looking at all these factors like oceanographic factors, gravity, and vertical land motion, all going into these projections, which were used for the NCA4. These new projections that came out for NCA4 were anchored in year 2000 instead of the previous scenarios, which were NCA3 were actually in 1992, which was the middle of the tidal epoch. These started in 2000, and for every decade out to 2100, they actually go out to 2200. But you can see they also provided some probability analysis, looking at this red box that I drew here is kind of the higher probabilities of where we may end up within this distribution. So these scenarios kind of slice through the probability distribution, with the red box there being kind of the more likely scenarios, somewhere between the intermediate low and intermediate high. And as you can see, that kind of is in the middle range of these RCPs I mentioned earlier. We do have to keep in mind that the RCPs themselves are scenarios, but so it's a little bit difficult to try to do probability for sea level rise, but this gives you an idea of maybe a potentially more likely. And then we can track that too using not only tide gauge information, but also since 1993, we've been using satellite altimetry to track what's going on globally with sea level rise. And this is just a snapshot of what's going on in the southern Atlantic coast. And you can see that, yes, it is variable. At any given time, we may be on one of these different scenario lines. And you can also see that it's not going to be a smooth curve that the projections are showing. It's going to go up and down. And this is, we're kind of following right along the intermediate scenario at this point. The big question for planners is, and local communities, well, what scenario do I use? We've got all these scenarios. We have the extreme ones. We have the lower ones. And what we try to do is kind of, we suggest taking a risk-based management approach, which is for areas that you have a higher risk tolerance, areas that have greater flexibility to accommodate flooding, open areas, parking lots, open spaces, then you may not need to plan for as high a scenario as you would if you have a lower risk tolerance, like showing here on the right. This is San Francisco Airport. Areas that have like critical infrastructure that cannot be flooded, or areas that cannot be cut off access to, for instance, emergency services, then obviously you want to be planning for a higher sea level rise scenario in the future. I'll give you an example, digging into the southeast a little bit. This is from the city of Charleston sea level rise strategy, which we have a case study in our chapter about this. They have decided, actually using the newer projections here for NCA4, they're planning out to 2070, so 50 years out, and looking at a 3-foot increase for critical infrastructure and a 2-foot increase. So sort of this is a freeboard. They want to have development take this into account when they're developing, almost like, and adding to freeboard to the base flood elevation. And you can see they're following right along that intermediate curve. And just to get into more of the meat of the actual NCA4, just kind of want to start at the national level with the coastal effects chapter. Their key messages are not only drive home for the Southeast, but all other parts of the country too, which is that, one, the coastal economies and the property are already at risk. Excuse me, we're already seeing a cumulative cost of sea level rise happening on the coast. It's already starting with things like higher storm surges than they were back in the 60s or so. We're seeing more dollar loss, trillions of dollars, and we're seeing impacts on property values. So under these higher scenarios, we think that these coastal communities are going to be transformed by this in terms of the economy, the local economies. In addition to that, for key message 2, the coastal environments are already at risk. Not only our natural environments, we're seeing, and I don't get into this in my key message, but we do talk about it in our chapter, and you'll hear about that, which is the environments are changing. For instance, the mangroves are moving farther north, but we're also seeing threatening our areas that our national security. For instance, this is the Norfolk Naval Base, and they're really dealing with it. The Department of Defense is really dealing with this. It's the largest Navy base in the world, and it's starting to have impacts from coastal flooding. And then third is the social side of things, the social challenge, which is the equity of this kind of thing. For instance, who pays for the risk? Who pays for the damage that happens for coastal flooding? For instance, if you're living in Iowa, you may say, I don't want to pay for someone's beach house on the coast if they get damaged. It's not our fault they're building there. So this sort of the social inequity, who's going to pay for the impacts? And we think that the coastal areas are going to be the first to really test this sort of the legal framework and policies that are going to have to come about when we are dealing with this and other non-coastal areas as well. So with that said, I'm going to dig right into our main key message here and get into this chapter 2. I'm sorry, key message 2, which is, I'll just kind of repeat it here, that in the southeast coastal plain, we have a lot of inland low-lying areas, and at the coastal plain, obviously low-lying, and they do support a very rapidly growing population. We've seen an incredible increase in population in the south. Most of those states, especially the coastal ones, have a tourism-dominated economy. We have critical industries, important cultural resources, and they're all very highly vulnerable. So the combined effects of the changing rainfall, which I'll talk about, and sea level is really combining to cause a lot more issues than we've seen in the past. And without significant adaptation measures, we feel like we're going to start to have daily problems, and we've definitely seen that in the last few years with the flood events. At the immediate coast, what's really driving this is we're starting to see an increase in even just the high tide flood events. Again, a colleague of mine, Billy Sweet's been doing a lot of work on starting to count the number of times we're having flooding impacts just from, not only from storm events, but just from tidal events like perigean tides, or another common word is the spring tides, or the king tides, which are the largest tides of the year. And you can see on this graph that in Charleston, we've had a large increase in the total number of days where we're seeing tidal and flooding impacts go above what we call like our flood warning threshold. And this is what it looks like for a lot of places. It could be sunny day, no wind, but yet the tide is coming up through the storm drains. And so communities like Charleston and Norfolk and Miami are having to deal with this now and going back and retrofitting their stormwater systems to put tide backflow preventers so the water won't come up through the pipes, but it basically comes up and you have seawater right there in the streets, which obviously is not good for undercarriages of vehicles. So this is becoming a big problem. And of course, if you add rainfall to that is another large problem. And so you can see one of the figures we try to show here is that this is up in Norfolk, that the whole distribution of these events is actually moving to the right, if you will. So we take a typical bell curve and you see the probability of occurrence, the highest water levels back in the 60s, the whole distribution has moved to the right with sea level rise. So if you look at the line here, the flooding begins at this line. And if you remember how to do your calculus, there's more area under the curve now in the 2010s than there was in past that line. So we're definitely seeing more extreme events occurring, and that's happening also with some of the rainfall events as well. Excuse me. And this is an example in Fort Pulaski, which we have another tide gauge down near Savannah, and you can see the number of observations of high tide flooding events have increased. And as we extrapolate that out using the sea level rise scenarios, you can see that we're eventually going to have almost every high tide is going to be causing significant flooding events. And so our mean high water of today and the future is going to have to be changing. And every tidal epoch, which is 19.6 years, we're going to see mean high water continue to rise. We've also seen an increasing amount of inland flooding events. This is just taken from some of the billion-dollar disaster data that our colleagues in Asheville NCEI work on, and that is we've seen an increase in the number of casualties and dollar amounts of damage from inland events. And this is just to name a few. And when we finished when we finished working on this chapter, we probably had 2 or 3 events we could have added on to this, including Hurricane Irma, and significant flood events like Hurricane Florence, which just happened last year. So these are not going to end anytime soon. We're seeing a definite increase in these significant extreme rainfall events, and the NCA4 also points to this in the precipitation, and that is that the frequency intensity of heavy precip events are going to continue to increase, especially if you look at these graphics in the southeast. So if you combine the rainfall events that this is just an example of that we talk about in the chapter, which is in 2015, we had this really large rain event. It wasn't even a landfalling storm. It was Hurricane Joaquin was way off the coast, but it was just sort of this Pineapple Express, if you will, of a train of rainfall coming into the coast, as well as really high tides we had. Perigean tides at the same time caused major flooding issues because the water just could not drain. So we had in the Charleston, South Carolina area, really big impacts, but also inland, places all the way up to Columbia were having problems because of the rainfall. And again, I mentioned this problem is that you have water trying to get through the stormwater systems normally, but then if you add tide influence in there, these systems were not designed to handle that, and so we're starting to see major backup issues. And another thing we address in the chapter is we kind of tipped the hat to the hurricane influence, and it ended up getting put in our chapter, which is the Hurricane Irma. The main gist of this is that the warmer water we're seeing with the ocean absorbing the heat is causing warmer water not only at the surface but at depth as well. So that's able to sustain higher intensity hurricanes, and we definitely see that even since Irma. We've seen more Category 5 hurricanes. So we don't know necessarily if the number of hurricanes is going to increase, but we do know with increasing depth and increasing heat content, we'll probably continue to see these high intensity storms. And sea level is going to just make these storms worse. I like this graphic. It's not from NCA4. I think I borrowed this from potentially Sea Grant or the Union of Concerned Scientists. I'm not sure which, but you can see that the 2010 floodplain is here, and there's a structure. And so if you think about your current floodplain maps that FEMA has, and then you add sea level to that, we're going to see an inland migration of the floodplain. And so these storm surge events are just going to get worse and worse. And by the way, the FEMA flood insurance rate maps do not take into account long-term sea level rise or long-term erosion. So something to be aware of when we're looking at our current flood risks. So this is a slide I put in there because this is all kind of grim information, but I think what we're also concentrating on in this version of NCA4 is communities are actually starting to take action and put into place adaptation measures. So we have some case studies. This is taken from in Charleston, where they have a sea level rise strategy. I already showed you the curves they're using and how they're building that into the planning. They're spending what money they can through different federal, non-federal sources to shore up, for instance, sea walls and add elevation to the seawalls. They're working on the drainage problem by doing tunneling and pumping, similar to what they're doing in New Orleans. They're having to start to build that same capacity for the smaller cities like Charleston. We also know, for instance, down in Tybee Island, which has a large, long causeway going out to it. It gets cut off during flood events, especially even high tide events. And so they're trying to go, and they actually have an adaptation plan, and they're going and trying to raise that causeway so it's less vulnerable. And this is another case study where a community in Louisiana, the Ile-de-Jean Charles tribal community. It's a pretty small island that has seen about 98% loss of their landmass since the 50s, and they received some HUD money on the order of like 48 million, I think, to help basically relocate this community. This is a graphic showing a community meeting. Hasn't been an easy process, and I'm certainly not the expert on this. Aranzazu was actually the one that helped me with this case study, and it's a good example of this is where we may have to see communities being relocated so they can still thrive and still have their social structure, but it won't be at the place where they kind of have that sense of place. So it's a definite traumatic process, but it's an example of where we may see this. There's communities in Alaska dealing with the same issues due to some of the coastal erosion. So with that, that kind of gives you a flavor for what information's in the chapter and some of the case studies. So I invite you to go in and the graphics are really easy to download, and they should be attributed, and the source of where everything came from you should be able to locate that and use that. So with that, I'll stop and I'll take any questions you guys might have.
Thank you very much, Doug. We really appreciate it. And thank you, in spite of having your cold, that you managed to show up today. So we really thank you. And again, Carrie is saying to please, you can funnel questions to us via the chat. You can also unmute yourself, I think, and ask your question directly to Doug. Okay, and then in the meantime, I just wanted to make sure I showed everybody. Doug wanted me to pull up the slide. These are.
I'm going to stop sharing mine. There you go.
Okay. Okay.
Yeah.
Can everyone see that?
No.
No. Okay. One second. Let me share my slide here. Great. Okay. Here we go. We just wanted to make sure that everyone saw this slide. It is the authors, and I think Doug wanted to give deference to the team that formed part of the Southeast chapter, and
yes.
And so thank you for that reminder, Doug. It was a great team, I have to say. It's a fantastic team.
It definitely was a good team. It was more, I think, more work than some of us thought, but it was rewarding.
It was rewarding. I think we got the chapter out even a little bit ahead of time. And then I just wanted to point this out to everybody. This is sort of a screenshot of the website for the NCA4. You'll see the URL at the bottom there, NCA 2018. That's a quick way to Google it if you have a hard time remembering the URL, just NCA 2018. You come to this landing page, and I put these orange arrows on the right-hand side to point out that the report chapters are a key way to query the report, and then the downloads should you need any of the graphs that Doug showed, or any of the graphs that go along with any of the chapters are meant to be easily downloadable so that you can insert them into presentations or grant reports or anything like that, as far as making a case towards climate adaptation work. And the report chapters are by region, but also by sectors, as Doug mentioned. So there's quite a few sectors in there that may be of interest to you. And then just quickly, here is volume 1 that Doug referenced. It's called the Climate Science Special Report, or the CCSR report. And then the volume 2 is what we reference as the NCA4, which includes the impacts, risks, and adaptation. So there you have it. And I just wanted to go back to our questions and make sure we have time to hear from anybody that's got any questions. And if not, Carrie and I can prompt anybody. Like, please go ahead if anyone has any questions for Doug.
And if you have trouble unmuting because you want to ask the question, just raise your hand and I can unmute you. Or use the chat box.
All right, so here is a question from someone, Francis. Is there anything in the report addressing the role of sea level rise and saltwater intrusion of coastal aquifers?
There's not a great deal of it in our chapter. I think if Mike Oslin's going to be
yes
next, he's going to be addressing some of more of the ecological impacts, and he deals with a little bit of that in his part of the report. Especially, it's become, we didn't have someone on our team with the explicit expertise in groundwater, and it's something I think we're going to, every time we get back, it's a 4-year process. So when we go back, we'll try to concentrate on things we didn't concentrate on last time. That might be something we want to look into. I know in Florida, for instance, with the karst geology there, it's a really big issue because you got water coming up from the bottom as well. Obviously, fresh water floats on top of the salt water as it comes in, and that's going to raise the water table, and it also causes issues with drinking water too. So, but again, it's mentioned in the key message 3 a little bit. So I'd encourage you to tune in for that one. Is that next month?
Doug, that is. Yep.
Okay.
And I'll pull up a slide for the date for that one in just a minute. Yep.
So I have a question. Hopefully I can articulate it in a way that makes sense. So I know we've talked a bit about surface sea temperature and that influence on rising sea levels. Are changes in freshwater stream temperature, which we know have obviously ecological effects, but is there a direct influence on some of the inland flooding with rising temperatures in freshwater streams?
It's a good question. So one thing we do know is that with an increase, I guess, of about 1 degree Celsius in the atmospheric temperature, that the atmosphere can hold about 7% more water vapor. Mm-hmm. And so we think that's what's leading to these potentially more extreme rain events, is that the atmosphere gets just more moist and could precipitate out more water, precipitable water. There's been a lot of back and forth in the science on looking at, for instance, the USGS has done a lot of work on looking at the stream gauge data to determine if we're seeing an increase in the flood events, the actual discharge of the streams, and what they're noticing, not necessarily in the mean, and same with the precipitation, it's the mean sort of average isn't changing as much as the extremes are. So if you think of that sort of bell curve we looked at for sea level rise, if you think the bell curve, it's the right hand side is where the extreme events occur, and that's where we're seeing it start to change. Mm-hmm. So they're thinking we're going to see an increase in more of the extreme events, which is going to lead to eventually increasing stream runoff. And I think that the problem with hydrology and climate change is that you have to isolate the variables, right? So is it land cover or is it land use change that's causing increasing runoff and stream discharge, or is it climate change? That's a tough one. So what they try to do is look at the stream gauge data to see if is there a signal in there that's signaling non-stationarity, which means we've seen a definite change in the distribution in the last, let's say, 50 years versus the before that, and that the distribution's kind of changing and moving to the right. So it's an emerging science. I would say the hydrologists recognize this too, that there's not as much actionable science that can be applied for adaptation on the hydrology side of things as there is for things like sea level rise certainty. So it's an area that's continually being worked on, and trying to parse out the stream gauge data to figure out if there's non-stationarity going on. I think the Corps of Engineers has a really good tool that can do that. We're starting to look into that. So, so it's a combination. We'll see increasing runoff from more development and impervious surface, in addition to changing precipitation patterns. So it's hard when you have two variables changing at the same time.
Yeah, great, thank you.
Thank you, Doug. Any other questions for Doug? Maybe I'll ask a quick one here, Doug. So does does some of the flooding, inland flooding, take into account, Doug, what we at least saw here in North Carolina was that for some of these heavy precipitation events, whether they're storm driven, you know, everything is draining towards the coast, right? So at least North Carolina, everything is draining, towards the Atlantic, so eastward. And so by the time that, you know, everything is draining down, these coastal communities are seeing these really prolonged flooding events. And I wonder if some of the model, I guess I just wonder about that particular scenario of, you know, you can do some modeling on the coast, but does that ever consider, you know, not knowing sort of that you might have a lot of water just draining
Right.
towards the coast?
Yeah, it's a great question. And to be honest, like NOAA has been really, well, more recently, we've really been focusing on this issue. It's something that I think the disciplines are kind of always operated separately. The hydrologists would worry about the riverine and do river forecasting and not take into account what's going on at the coast. And then on the coastal side, you had estuary modelers looking at storm surge and hydrodynamics of the estuaries, but they didn't take into account the river discharge coming down. So we're starting to see a big effort to try to couple the riverine and the coastal models together.
Mm-hmm.
One thing I'll mention is that there's a brand new, it's several years it's been there now, but brand new, it's called the National Water Center, and it's actually on the campus of University of Alabama in Tuscaloosa. And it's a combined effort with USGS and NOAA and Corps of Engineers and FEMA. There's primarily mostly Weather Service folks there, though, working on the National Water Model. And what they're trying to do is work on a model that will allow them to forecast on all segments of the stream, not just at forecast points. So, the way things are done now is there's these forecast points that are really based where we have gauge information, and they'll do a forecast at that particular point. What they're trying to do is be able to forecast along all the river reaches, including those that don't have stream gauges, and then also couple that to what we are doing, what other part of NOAA is doing at the coast. So the idea is you would be able to take into account, a great example was, I can go back and think of Hurricane Floyd in 1999, which is probably similar to Matthew and Florence on magnitude, but there was a previous hurricane was sticking around. I think it was Dennis, had raised a lot of the water levels in the sounds, for instance, Pamlico and Albemarle Sound. And then when Floyd came, we already had elevated water levels, and then you had additional storm surge and rain. So it's this sort of antecedent conditions can also add to the flooding issues. And so if you're not taking that into account every time you're doing a model or, a new event, you could definitely get it wrong. So the modeling's definitely has been leaps and bounds better than it has been, and I think we're going to start to see, hopefully better forecasting coming down due to that.
Yeah, thanks for that information, Doug. That's great, because that also helps feed in some potential interesting research partnerships.
Yep.
Right. All right. Any other questions? Did you have one, Carrie?
Yeah. So, Doug, you mentioned that you're currently sort of tracking, mean global sea level rise. We're using tide gauges and, satellite altimetry as sort of the two main data sources. Are there, sort of looking ahead to making better predictions or whatever? Are there some areas in there that you would see as points where additional data or research or technologies would be helpful in sort of trying to continue to estimate sea level rise going forward?
Well, yeah. So the global network of gauges is definitely helps, and of course, before satellite technology, that's all we had, and so there's a concerted effort globally to to capture what's going on with water levels. And there's a service called I think it's called the Permanent Sea Level Rise Service or something that I believe the data is stored in Hawaii. So it uses the tide gauges from all over the country and puts it into a format that's standard and consistent and QA'd. And that helps with establishing the global trends. And then, like you mentioned, the satellite data, there probably is going to be a new technology, or they'll improve the satellite technology to be able to remotely sense what sea level is doing. And then I think that what we're seeing is in terms of the projections, the biggest, as I mentioned, the biggest uncertainty has been the ice sheets. And we have not really had, because, and this is based on opinion, I think, for me, but I think we didn't really study the ice sheets before things were pretty stable with sea level, because, you know, there were hard places to get to and they're expensive to get to. And we didn't have any real models developed to figure out how the ice sheets are going to melt, you know, the grounding line and all that stuff, how the whole system functions. And so every year we have more data coming out of places like Greenland.
Mm-hmm.
You know, that's being used to calibrate it and build these ice sheet models to figure out how fast is that mass going to be transferred to the ocean.
Mm-hmm.
So I would, if there are students out there, I would say if you want to go into ice sheet science, there's probably plenty of jobs for that in the future, because it really was something that we weren't concentrating on, and now there's obviously a big push for that. So if you look at some of what the sea level rise scientists, like some of the big names like Church and those guys, that's really what they're focusing on, is that the hardest thing to pin down with sea level projections is that end of the curve on the right side, as I mentioned, with that distribution, the extremes. How high do you put the projection? That highest curve, which we call the extreme in NCA4, is basically just acknowledging that we don't know how fast ice sheets are going to melt and how much they're going to contribute and by when. So let's put that number up there because there's so much uncertainty with it. We just want to make sure we're going to be prepared for the worst case. So I wouldn't be surprised the more we learn about ice sheets that extreme curve, as we continue to update NCA process, next will be NCA5, you may see it even go higher. So I didn't directly answer your question. As far as new remote sensing techniques, I'm not aware of any, but obviously the more in situ readings we can get. And another one, though, I'm kind of thinking out loud as I'm going here, is the subsidence issue. So I mentioned vertical land motion is a huge component to local sea level rise, and that's something that both NASA and NOAA are trying to get at, because we don't really have a good national view of land subsidence. So they're investing in new technology called INSAR, which is satellite based, to look at where are the areas we have hotspots in the subsidence, and if we can get like a regional gridded type product for that will really improve the local sea level rise projections. So right now we're relying mostly on the vertical land motion. We're measuring at the tide gauges, so it's very local. And it can vary, as you can see in the Gulf, you know, pretty quickly between states. So if we can get a surface of that through a gridded kind of modeled subsidence product, that would really help.
Thank you, Doug. And you had mentioned, Doug, a tool that maybe you might suggest to the group if they're interested in doing, maybe perhaps might reveal some visualization.
Yeah, I can. Would you want me to share again?
Sure.
Okay.
Please do.
All right. I can mention a couple here.
Sure.
Let's see. Well, actually, let me get out of this.
Sure. And while I have a second here, I just wanted to pull up this for everybody, and I'll leave this with everybody up. But our next key message webinar, key message 3.
I'm not sure.
Oh, okay. Sorry, I'm not sharing. I wasn't sharing at that moment. The challenge of multiple presenters of it.
Okay, sorry, let me, I had to get out of my presentation. Now I think I can share again.
Okay.
Well, sorry about this. I'm having a tough time getting back into to be able to share it.
Yeah, we're not seeing you again.
Okay. Where is? You guys can still hear me, right? For some reason, I think I got kicked out of where I can actually do the sharing for some reason here.
Oh, okay. Yeah, we can hear you, Doug. Yep.
Okay. I'm not sure how to.
Here, I'll make you a co-host.
Do you see that there's the little share, the little envelope that's green?
Yeah, but
So this made you a co-host, which may increase your capabilities.
right. I'm sorry. I don't know. Yeah, some reason like it doesn't let me.
Okay.
It wants me to join in and get the meeting again for some reason, but I guess you can still hear me.
Yeah, we can still hear you. Okay.
Let's see.
Well, we can also just add some tools onto.
Yeah, if you have a link, you can paste them into the chat box as well.
Right.
Doug, if that's a.
You can type in the URL to the particular tool, if that's helpful.
Why can't I? It's telling me, like, I tried to get Zoom on here, and it's telling me I'm not signed in, which is weird because I'm. Let me try to get back into the meeting, and that might help here.
Okay. Meanwhile,
let me just share with everybody real quick before we lose any more people here. Just wanted to give everybody a heads up that our Key Message 3 webinar will be November 20th, and that will be delivered by Mike Osland. He's an ecologist with the USGS, and some of you had asked a question about impacts to natural ecosystems, so that's one to definitely sign up for. And then you can visit our website for any more information at secasc.ncsu.edu. And please do sign up for a newsletter if you're interested in more information about what we do and opportunities and conferences and publications and data and tools. Please sign up for our newsletter, which is on that Go link at the very bottom.
I'm back. Can you guys hear me?
Okay, Doug.
Yeah, if you stop sharing, I should be able to share it.
Okay, very good.
Okay.
Oh,
There we go.
There we go.
Should be able to. Okay. So this is I go to Digital Coast. Okay. Can you see this now?
Yes.
So let me get rid of this thing. Okay. Yeah. So this is our office website, Office for Coastal Management. This is sort of our homepage, and you can. We do various things. We manage the coastal zone management program for the country. We also do coral reef conservation, manage the natural estuarine research reserves. But then if you go here to Digital Coast, this button here, we have a lot of data. For instance, all the elevation data, the LiDAR data that is collected around the coast. We host a lot of that on our site. We have land cover data as well, and some imagery. We have a bunch of tools. One is our sea level rise viewer. You go to this page where it kind of gives you an overview of what the tool does. You can go to download the data or access map services if you're a GIS person, so you can pull them in. where you can launch the tool. And we get a lot of communities using the data behind this. So if I just want to do, I can look up Charleston since that's where I'm right now, Charleston, South Carolina. Zooms in on it. Let's kind of go closer. See, we have these landmarks here. And for instance, that's the Customs House in downtown Charleston. And we have current mean high water, which is mapped here. And then we can raise water level by 1 foot increments. Again, this is using the best available elevation data we have. And this shows you what would be impacted at various water level heights. And you can change this to feet or meters. And the main thing I was wanting to show you here is that we've incorporated the NCA scenarios into this tool. So you click on the closest tide gauge, and you can kind of see if you zoom out where the tide gauges are located. There's one up at Myrtle Beach, there's one in Charleston. If you go up in North Carolina, there's one in Wilmington. And here's the one in Beaufort we were talking about earlier. So you select that, and then you can go zoom into the community. And what it's doing is using the information that the local relative sea level rise projections for that community. I'll zoom into Morehead City, for instance. Then you can do a comparison on the different sea level scenarios, like the high, the intermediate, or you can do it by year. So if you want to plan the 2080 horizon, planning horizon, and here's the different scenarios on your left, then you can match the inundation to those and see what would be impacted at the high scenario by 2080. So it gives you not only what's going to be flooded or what would potentially be impacted, but when is it going to happen and what scenario is going to cause that. So it's just kind of a different way to visualize. If you think about all the curves being right now in 2000, they're all starting out at the same location, and as you go out, it's just a different way to visualize the curves kind of spreading apart. So you can see there's a big variation between the extreme and the low, almost a 10-foot variation. So that's where that whole uncertainty of what's going to happen in the future. So that's a neat tool. And then you can go up here and go to download for your area. If you want to go to North Carolina, here you can download based on what county you live in, and all the data is available, as well as the actual digital elevation model we use to do the mapping. So that's a pretty popular tool. I guess we're getting close to the end here, but you can also just peruse some other tools on our digital coast. We have a coastal flood exposure mapper is another one that looks at both FEMA flooding maps and some of our stuff and storm surge, like worst case storm surge, and kind of gives you an idea of sort of the graduated risk that you have based on if you're closer to the water, you have a higher risk of being impacted. And the farther away, you have a less of an impact. And that it's not just a line, or if you're in or out, there's more of a graduated risk. So I guess I'll leave it at that. Sorry for the technical difficulties there for a minute.
No, not a problem. Thank you. Thank you that we're able to sneak this information in there. That's wonderful.
Yeah.
Yeah, it seems like for city planners, local county governments, this would be a really helpful tool.
Yeah, and we're also, just one other thing, we're pulling in this high tide flooding information from the high tide flood report. So you can get a chance, if you click on a particular tide gauge, you can see here the number of flood days we're having per year. And that shows you this red area actually was what would be impacted at that particular level. So that's the idea that we're having these these high tide flood events happening more and more often because of sea level rise. So it's a great indicator as we go forward with climate change, even in the NCA process. We're always looking for indicators of sea level rise, and this is a really good one.
Mm-hmm. Mm-hmm. Yeah, that's fantastic. Thank you. Thank you.
You're welcome.
Doug, really appreciate it. Well, with that, we really thank you, Doug, again so much for participating in this webinar for us. We really appreciate it.
I was happy to do it.
And wonderful. And again, I'm just going to leave everybody here with the information for the NCA4, the URLs, and please do sign up for our newsletter and join us next month on November 20th. And by the way, we'll also post a recording of this on our website should you want to refer to it again or refer others to it. It serves as a resource as well.
Awesome. Thank you.
Thank you, everybody. Thank you for joining us.